Bismillahirrahmanirrahim. This lecture is about the real gases or the behavior of the real gases, and we will talk about the van der Waals equation. And this equation is going to brief the behavior of the real gases. So in the previous video, you have already learned the kinetic molecular theory, which is based on the following assumption. Two of them are mentioned over here because relevant to discuss the behavior of the real gases. So the first assumption is the volume of the particle of the gas themselves is negligible compared with the total volume of the gas, and most of the volume of a gas is empty spaces. So uh, this is particularly with reference to the ideal gas. So now the real gases are going to deviate from this assumption, and this is the our one of the main objective of today class, to learn about how the real gases are going to deviate from the ideal gases based on this assumption. And the second assumption is the gas particle act independently of one another, and there are no attractive or repulsive forces between the particles. So again, this is for the ideal gases, but we will look today, and we will discuss about the what type of the forces are going to exist between the particles, and how the real gases are going to deviate if there is the attractive or the repulsive force of forces are present between the particles. So this is uh, all about the main objective of today class, and we will look into two main issues or the problems which are related to the real gases as compared to the ideal gas. So here is the behavior of the real gas is different from the ideal gas because of the two problems, as in the previous slide I have mentioned about the kinetic molecular theory. And the first one is the having the real gas is having volume at high pressure, and the real gases are having the attractive forces between the particles. And these are the two graphs we have already studied and discussed in the previous lecture. That means if the gas is the ideal, and this is the compressibility factor, and it is having the value of the 1, and when it is the ideal gas, the value will remain the 1 throughout the pressure. If you increase the pressure, there should not be any increase and decrease of the behavior of PV over RT, because this is the compressibility factor. It will remain the constant. That means the gas is the ideal gas. But all these are the real gases. When you increase the pressure, there is the more deviation from this ideal behavior, and this is our today objective, to discuss this deviation and to derive the equation, to have the equation which is going to fit the data for the real gases, and this is the van der Waals equation. Similarly, if you have a different temperatures, so the gas molecules are also going to deviate, and again, what is the difference of the between the real gas and the ideal gas over here? And this is again the compressibility factor. It will remain constant if the gas is the ideal, but as soon as you to give a different temperature to a gas, there is the deviation. And look at the temperature. As the low temperature, there is more deviation as compared to the high temperature. Again, these two deviation we have already discussed in the previous video, and please go to the lecture to watch them again to clarify this concept. But here the purpose of showing these two graphs is because when there is the uh, high pressure and when there are the intermolecular forces, now the the real gas is having some volume and they are having the attractive forces between the particles, and this is the gas law. Previously we have derived by using the Waals law, Charles law, and the Avogadro law, and this is the equation is the P is equal nRT, and this is the van der Waals equation. Actually there is the addition of this factor to the pressure and the subtraction of this factor to the volume, and nRT is the same in the both equation. And in today's lecture you will learn about how this factor is coming out uh, to the equation, and this factor as well to discuss the behavior of the real gas. So this is for the ideal gas and this is for the non-ideal gas, or you can say this is for the real gases as well. So the first is the that mean you have to correct the pressure and you have to correct the volume. So when you correct all these pressure and the volume for the real gases, you can you can get the final this equation, which is called the van der Waals equation. So the first I'm going to discuss over here the volume correction. Why the real gases are having the volume and what is the reason? So how you can correct that volume by using some certain parameters. So, for instance, again, the kinetic molecular theory assumes that the volume of the gas particles themselves is negligible as compared to the total volume of the gas. So, this is for the ideal gas. But what is happening over here? Uh, the this assumption is valid at the standard temperature and the pressure. You know, standard temperature and the pressure is the temperature is 0 degree centigrade and the pressure is the 1 atmosphere. So here we are taking the standard temperature, but what is happening with the increase or the decrease in the pressure? So where the volume taken up by the molecules of the typical gas is only 0.05% of the total volume. This is at the standard temperature and the pressure. So what is happening over here? The volume uh, taken up by the gas molecules is on only 0.05% of the total volume, and that means this is going to very close to the ideal behavior of the gases. But what is happening over here, this assumption is not valid at the higher pressure. So when you increase the pressure from 1 atmosphere to the 500 atmosphere, so this assumption is only at the standard pressure, which is the 1 atmosphere. So when there is the non-standard condition, and that means the pressure is not 1 atmosphere, if you increase the pressure to, let's suppose, the 500 atmosphere, now the volume of the gas molecule is 20% of the total volume. That means no, you cannot neglect this volume as compared to the total volume. That means as a result, volume of the real gas at high pressure is larger than predicted by the ideal gas law. So this is the let's suppose this is the behavior of the gas particles, which is less important at the lower pressure as compared to the high pressure. So when you increase the pressure, now the volume of the real gas is the higher as compared to the ideal gas. That means now you have to correct that volume, and this I will be discussing in the next slide. So the first is to understand why the correction is required in case of the volume, because we have the two variable pressure and the volume, and I have discussed over here why the correction in volume is required. Now coming to the correction in pressure, and this is due to the attractive forces between the particles. So again, uh, this is the second assumption of the kinetic molecular theory, that which is going to discuss that there are no attractive forces between the particles. And but what is happening with the real gases, the molecules, these are the molecules, they may attract one another at about the 10 molecular diameter, the distance at about 10 molecular diameter, they are going to attract to each other. So as a result, there is the decrease in the actual volume of the gas, actual volume of the, that means the real gases, as compared with the ideal gases at pressure up to the 300 atmosphere. So because these molecules are going to attract to each other, when there is the attraction between these the particles, and they are going to, there the pressure is going to be less as compared to the pressure of the gases, because the pressure is actually what when the molecule of the gases are randomly moving in a box, and when they exert a pressure on the walls of the container, that means this is called the pressure of the gas. And when the molecules are going to attract to each other, that means then they have the less collision of these particles with the walls of the container. That means this is going to reduce the pressure, and this is happening in case of the real gases, because we are going to assume there are no attractive forces between the ideal gases. So ideal gases will exert more pressure, but in case of the real pressure, real gases, due to the attractive forces between the particles, they have less collisions at the wall of the container, and that's why they are going to have the less pressure. So this is explained over here. At low pressure, this assumption is good because the gas particles are so far apart. So if there is no attractive forces, that means this can only be happen at the low pressure, because at low pressure these molecules are or the atoms are moving randomly. They do not have the attraction between them. But at high pressure, the particles are much closer together, and uh, and have the attractive forces between them, and the forces become more important in case of the high pressure. So when you increase the pressure, the molecules are coming together, and then that means they are having the attractive forces as compared to the ideal gas behavior. So this result, due to the attraction between the particles, this result is to draw the molecules together slightly, decreasing the volume at a given pressure, or decreasing the pressure for a given volume. That means if there is the attraction between the molecules, so if you would remain the pressure as a constant, then there should be a decrease in the volume. And if you remain the volume as a constant at a given volume, so due to the attractive forces between the particles, the pressure is going to decrease. So that means now you have to correct that pressure, and how it is happening I'm going to explain in this slide. So what we have discussed right now, the effect of the molecular volume, that means to increase the volume, is opposite that of the intermolecular attraction to decrease the volume. That means by increasing the pressure, in the first assumption we have discussed, there is the increase in the volume. That means you have to correct that response. And due to the intermolecular attraction, there is the decrease in volume. So when there is an increase and there is a decrease in the volume, so these two factors therefore tends to cancel at the intermediate pressure. So this is actually what is happening over here. But the effect of the molecular volume dominates about above 350 atmosphere, again when there is no standard temperature and the pressure conditions. So this effect is not going to be cancelled out. Now you have to correct the pressure and the volume. So the first, both problems can be dealt with with mathematically by modification of the ideal gas law, and this is called the van der Waals equation. And this is going to use the two correction factor. One is the small a, another one is the small b. One is associated with the pressure, another one is associated with the volume. So let's suppose what we have discussed in the previous slide, there is the increase in volume at the high pressure. So we are discussing over here, this is the correction in volume. When the pressure was higher, then there is the we have the increase in volume at high pressure, because the volume now is not negligible for the real gases at high pressure. So this is caused by the effect of the molecular volume is corrected by subtracting an amount and b from the observed volume. So this was the actual volume, and now the volume is increased in case of the real gases. So you have to subtract that amount from the volume to correct this volume. So the minus sign is being used because there is the increase in volume at the higher pressure. So that's why you are going to subtract this from the actual volume to correct the volume. So the decrease in volume, actually this is going to equivalently decreasing the pressure due to the intermolecular attraction. So when there is the intermolecular attraction, and at a given volume the pressure is decreased, or at a given pressure the volume is decreased, and this is caused by the effect of the intermolecular attraction, and is best corrected by the adding an amount a n square over v square to the pressure. So what important over here is, because the pressure is decreased due to the intermolecular forces, so you have to add to correct that pressure which is in the ideal gas equation. So you have to add, because the pressure is decreased, by this factor a n square over v square. So a and b are the constant for the correction of the volume and the pressure, and here n is the number of moles, again n is the number of moles, v is the volume of the gas. So this is the all about the correction of the pressure and the volume. Now look at the final equation. What is the van der Waals equation? This is the ideal gas equation. PV is equal to nRT, and we are going to correct the pressure and the volume by adding this factor over here, and this is the correction in the pressure, and you can add subtract this for the correction of the molecular volume, and this equation is called the van der Waals equation. So actually there is addition of this factor and this factor to the ideal gas equation, which give you the van der Waals equation. So this equation for the ideal gases and this equation for the real gases, and simultaneously now you can calculate the pressure out of this. Similarly, you can get the pressure and the volume from the ideal gas equation. If from the ideal gas equation, P will be equal to nRT over V, and similarly you can rearrange this equation to get the pressure of the real gases, and this will be equal to nRT over V minus NB minus an square over V square. So this is very simple. First you have to divide, because this is going to multiply, and this is going to be divided with the nRT over n minus V minus NB over here, and then this is in the addition, when it moves to the right hand side, it will become in the subtraction sign, so minus sign should be there. So this is just very simple rearrangement of this equation, and you can calculate the pressure. So in the next we will see to calculate the pressure in case of the ideal gas and the real gases. So what would be the deviation in case of the real gas as compared to the ideal gas? So here again, a small a and small b. A is the attraction between individual gas particles, and b is the average volume of the individual gas particles, and these are the units of a and b. A is having the unit atmosphere, the liter square per mole square. So easily you can get the unit out of this equation, and this is the when you solve this individually, and when you take the value of the n, this would be the p v square over n square. So p is the pressure, v square is the liter, the volume is liter, and this will be the number of moles, the n is the number of mole, and it is the n square, that's why it is the mole square. And similarly you can get the unit of the b from this simple equation, and b will be equal to, when you move to the right hand side, it will be v equal to nb, and b will be equal to v over n, and the unit of v is the liter because this is the volume, and the unit of n will be the mole, so it will be liter per mole. So these are the units for the a and the b, which are constant, and which can only vary from one gas to another gas. So this is all about our today lecture, to discuss the real gases, or to find out the equation, and this equation is called the van der Waals equation, which is going to fit the data of the real gases.